Hi everyone, today I would offer my third lecture on the transformation of stress and strain. Before we begin today's topic, let me give you the review of a previous lecture as I have been doing as always. So in last lecture we discussed about three topics. First we discussed about principal stress and maximum shearing stress concept. So I put principal stress discussion on the left and maximum shearing stress discussion on the right. So the principal stress is defined as the state where we don't have any shear stress component. Then we call that axis as principal axis, and we call the normal stress in the absence of shear stress as principal stress. Okay, we after defining the principal stress, we discussed about how we can obtain the principal axis and principal strain. No, principal axis and principal stress. So what you do is following. First of all, as always, we complete the Mohr circle using x position and the origin and y position, and then because the vertical reading indicates the tau x prime y prime in new coordinate system, to make tau x prime y prime equals to be 0, yeah, we have to locate our x prime and y prime, on the sigma axis. Okay, so for that we have to have like 2 theta p rotation, and from the equation we derived, or from this geometric relationship, we can find the expression for tangent to 2 theta p, which is given as 2 tau xy divided by sigma x minus sigma y. Okay, so you can derive this either from the equation or either from trigonometric equation relationship using the Mohr circle. Okay, so and regarding the normal stress, the principal stress, we already know the sigma average value here, and we already know the radius of the Mohr circle, which is given as this. So principal stress is either sigma average plus R or sigma average minus R. Okay, so you can find the principal stress easily and the axis to find the principal stress. And then we discussed about maximum shearing stress. The reason why we discussed about principal stress and maximum shearing stress is that brittle material fails under the maximum normal stress condition, and the ductile material such as rubber or metal, like a metal such as copper is ductile material, and they typically fail under the shear. So if you find the maximum shearing stress value and maximum shearing stress plane, then you can predict the failure of ductile material. So maximum shearing stress occurs when x prime y prime aligns completely vertically, because at that position we have the maximum reading of the tau value. Okay, so this occurs when sigma x prime sigma y prime equals to be sigma average, and from the equations or from the geometrical relationship we can find the required angle 2 theta s from in this equation. Okay, and of course the maximum shearing stress can be quite easily found, because we already know the radius of the Mohr circle, and the radius of Mohr circle can be the maximum reading that we can have as a tau xy, tau x prime y prime. Okay, and it's given as R of the Mohr circle. And please remember that this discussion is limited to plane stress. So after we declare that this is limited to the plane stress problem, we discussed about second topic, the general stress state topic. So in general stress state, what I have learned was following. So we just learned that for a given xy z coordinate system, and suppose that we have 6 independent components of the stress, and we considered the quadratic form for sigma n, and based on linear algebra, even though I didn't give you the proof, we are always guaranteed to find the x prime y prime z prime axis, this orthogonal axis, such that all three shear stress component is 0. Okay, so this is the general stress state case and based on the linear algebra, but we didn't offer the full discussion considering full general cases. Instead, we consider a simple case and specific case where we can apply the Moore circle concept in 3D. So we don't know how to find the principal stress for general stress state given. However, if the principal stress is known, three principal stress is known, then what you can do is based on this three principal stress, you complete three circles, and if you fill up this shaded region, this shaded region means the combination of sigma and tau that this six stress component value can have, and each circle indicates the rotation about x prime axis, rotation about y prime axis, rotation about g prime axis. If sigma x prime, sigma y prime, and sigma g prime is given like this. Okay, so when you have a circle that connects sigma y prime and g prime, its rotation about g prime axis. When you have a big circle connecting sigma x prime and sigma g prime, it's about rotation about the y prime axis. Okay, so after you understand this the meaning of this Moore circle in 3D, actually we can apply this Moore circle concept to principal stress, to plane stress problems, because in plane stress problems we always guaranteed to have sigma z equals to be 0, and this rotation only is about the rotation about z-axis. So actually, in addition to these two principal stress, we always have sigma z equals to 0. So by completing the three principal axes, we have 1, 2, and 3 circles to complete the 3D Moore circle, and starting from here we can predict the maximum shear stress in full three-dimensional rotation. Okay, so with that, let me finish my review on previous lectures. And because we learn about Moore circle in 3D and the concept of principal stress and maximum shearing stress, in today's class we'll try to utilize the concepts we covered in previous lecture.